Hello everyone, welcome back to a new section from chapter 5. We have spherical mirrors. Very basically we're going to explain them. We don't have to go into the detail to each of them. There are two types of spherical mirrors. We have concave mirrors and we have convex mirrors. Concave mirrors are called converging mirrors. It means that light rays are going to be converged or collected at one point. For convex mirrors, light rays are going to be diverged. It means they're going to spread out. They're not going to be collected at one point. Concave mirrors are used to have an enlarged or a larger image than the object. And convex mirrors, they're used to have a smaller object, a smaller image than the object. You might have seen the application of a concave mirror while you're going to a dentist. You'll see that in the hands there is a small concave mirror that they use to see better or to see our teeth better. What factor determines the appearance of an image formed by a concave mirror? The radius of the spherical mirror. So when we are talking about a concave mirror, we have two things we should know. First of all, we have, let's say this is a concave mirror. The first thing we have is the focal length, and then we have something else called the center. Basically, focal length is half of the center. How do we get a concave mirror? Concave mirror can be created using a sphere. So if you go from the edge to the center, you have the center here. Let's say this is equal to 30 centimeters. And if you go half of it, it's going to be called focal length. This is basically 15 centimeters. Then we're going to have a concave mirror like this. We're going to get this here. We're going to cut this. We're going to polish this side and then smooth, or here, this is going to be a shiny surface. And this is going to be a concave mirror. So we have focal length and we have the center of the mirror. We have the difference between virtual and real image. A virtual image is when light rays are diverging. They don't collect, or they are not collected at one point. But with real images, light rays are going to be converged. So this is a rule. Anywhere you see that you have an image where light rays are converged means it's a real image. Another difference between them is that virtual images cannot be projected onto a screen. For example, if you have a phone and you have a convex mirror, you will see, or a plane mirror, you will see that the screen is not going to be, or the image on your phone is not going to be projected by the plane mirror or by the convex mirror. But if you have a concave mirror, and if you are holding the phone at a right distance, you'll see that the image on your phone is going to be projected onto a screen. Real images can be projected onto a physical screen, but virtual images cannot be. We have the three equations. When we are trying to predict the location of an image, we'll be using this equation, 1 over p plus 1 over q, which is equal to 1 over f, focal length. P is the image object distance, Q is the image distance, and F is the focal length, which is half of the center. When we are talking about concave mirrors, focal length and object distance are going to be positive. When we are dealing with convex mirrors, focal length and object distance are going to be negative. Careful. If we are dealing with the magnification in terms of height, we will be using this one. Magnification is equal to, if you want to know how magnified is the object, we're going to calculate it like this in terms of height. Image height divided by object height. In terms of height, in terms of distance, we're going to say m is equal to minus q, which is image distance, divided by p, which is object distance. These are some real important notes that you should know. For an image which is in front of the mirror, magnification is going to be negative and the image is going to be inverted and real. Whenever, this is a rule, whenever an image is inverted, it's real too. When the image is behind the mirror, magnification is going to be positive and the image is upright and virtual. And this is a rule too. Whenever an image is upright, it's going to be virtual too. If the magnification is greater than 1, then the image is magnified. And if it's less than 1, it's diminished or smaller than the object. These three rays are really important. When we are dealing with the image formation by a concave mirror, we have three rays we should know. So this is a concave mirror, this is the focal point here, and this is the center. If a ray is coming and it's parallel to this is a ray, and it's coming, it's parallel to the principal axis. This is called principal axis. Principal axis. If a ray is coming and it's parallel to the principal axis, it's going to be reflected through the focal point. If a ray is coming, but this time it's going through the focal point, okay, it's coming and it's going through the focal point, it's going to be reflected parallel to the principal axis. What if a ray is coming through the center? If a ray is coming through the center, then it's going to be directed through the center without any change in the angle. So we have three rays. Parallel to the principal line is going to be reflected through the focal point. If it's going through the focal point, it's going to be reflected parallel to the principal axis. If it's going through the center, it's going to go back through the center. These three rays are really important. You should know them. Then we have something really important here, which is the magnification of an image by a concave mirror. We have a concave mirror here. This is a convex mirror, and this is a concave mirror. We have an object, a candle, and then here we have focal point, and then we have the center too. So if we place the object, you might see this in your book. There are, I think, 6 image formations by concave mirror, but believe me, they're easy. Just look at the simulation. It's going to be really easy, and if you want to memorize them later, they're going to be really easy. If an object is placed outside the center, this is the center, by the way, the point or the place where the candle is right now. If an object is placed outside the center, the image is going to be inverted first and real. Remember, look at the candle, it's inverted. Now the image is outside the center. So the image is going to be real and inverted. Magnification here, as you see, the image is smaller than the object. You see, the candle is upside down and it is smaller than the object. Here, magnification will be less than 1, and the image is real and inverted. Careful. If we go further, you see, the candle is going to increase its size. The image, is going to increase until it becomes the same. So if an object is placed at the center, this is the center where the candle is right now, the image is still, careful, the image is still real because it's inverted, but the magnification here is going to be equal to 1. Here, when it's outside the C, when it's outside the center, it's going to be less than 1. As you see, the image is smaller than the object, but when I place it at the center, it's going to be 1. So the image and the object will have the same size. Here, the object is real and it's inverted with a magnification of 1. If the object is between here, the center or the focal point, it's going to be still real and inverted, but with a magnification greater than 1. Careful. As you see, the image now has a greater size than the focal point. If you go further and further, you'll see that the image is going to disappear. You see those two rays, they're having a greater distance between them. You see, the more I go close to the focal point, you'll see that the rays are getting further away from each other. If an object is placed between the focal point and the center, the magnification, as we said, is going to be greater than 1, or as you see, the image is greater, has a greater size than the object, and it's going to be inverted. I told you it's a rule: if an image is inverted, it means it's real. Then the image is going to be real too. Let's put the object at the focal point. You see, there is no image formation. Careful. If an object is placed at the focal point, no image is formed. If an object is placed inside the focal point, you see here, as you see now, the object is placed behind the focal point, we can say, or we can say in front of the mirror, but it's better to say behind the focal point. And this time, the image is upright. So you know, I told you, when an image is upright, it's going to be what? It's going to be virtual, with a magnification greater than 1. Still, you see that the image has a greater size than the object. I'm going to repeat this so you understand this better. That line you see here is the center. Careful. This is the focal point, half of the center. If we place an object outside the center, it's going to be inverted and it's going to be real, with a magnification less than 1. As you see, the image has a smaller size than the object. If you go further and further, or closer to the center, you will see that the image and the object have the same size. It's still inverted, so it's real, and the magnification is equal to 1. Careful. If we place the object between the focal point and the center, the image is going to be inverted, but with a magnification greater than 1. Careful. And it's going to be real. If we place the object at focal point, no image is formed. Why? If you are asked, why no image is formed at focal point? Because you see that those two rays, they are parallel to each other. They do not converge. Remember, when light rays are not converging, they're not going to form any image in concave mirrors. Careful. When the object is placed behind the focal point, then this time we're going to have a virtual image with a magnification greater than 1. I hope this simulation was helpful. If you want to memorize the 6 rays that we have, the 6 ray diagrams that we have, feel free to memorize them, but this simulation helps to memorize them faster. This is it. In the next lesson, in the next video, we're going to deal with calculating and predicting the location of an image by concave mirrors. See you in the next video.